Today we have 3 speakers I'm very happy about. It's about the task 40 of the TCP. The topic is compact thermal energy storage materials and components. As the first speaker, we have Andreas Hauer, who is the task manager of task 40. Following will be Stefania Doppiu, excuse me, and Christoph Rathgeber, which are both subtask leaders. Okay, with a short introduction, I would say, Andreas, the stage is yours. I will give the screen for you, if I know how to.
Thank you very much, Stefanie.
Just one.
Yeah.
Okay, here we go. Please.
Okay. Thank you very much. Now I have to open my presentation. Takes a second or two. Okay. So maybe I need a laser pointer. You never know. Okay. Just 1 second. I have to remove your pictures. Okay. Yeah, thank you very much for the possibility to talk about task 40. And actually, we have 2 subtask leaders here, as Stefanie said. They will go into detail, and I thought it might be interesting to have a look back and ahead, because this activity is quite unusual for the TCP. First, because it's a joint activity with the solar heating and cooling TCP. And secondly, it's an activity which has 4 phases now. This is the 4th and final phase. And we started some, I don't know, maybe 10 years ago. Yeah, so it's a quite long time that we worked on that topic, material research for compact thermal energy storage. And I would like to explain a little bit about things that happened before. So the scope of this activity is compact thermal energy storage materials. So it was clearly to see what are the possibilities of material research for this kind of thermal energy storage systems. And we looked and look still into 2 technologies, phase change materials and thermochemical processes. Just very briefly explaining what that means. So if we have sensible storage, and you have here a diagram where you have this stored thermal energy on the y-axis, and on the x-axis you have the temperature, then within a certain temperature range, temperature interval, you can store a certain amount of heat. Here we have the line for water, so all materials have different slopes here. If we look at phase change materials, and we have our melting point within this temperature range, we could probably store much more heat in this PCM phase change material. So that's the basic idea, to get higher energy content, higher storage capacity, or higher energy density. That's all the same, more or less. And thermochemical storage now is a chemical reaction where you have 2 components, A and B. And if you add heat, you separate them, you can keep them separated. And if you bring them together, you get the heat back. So you have a heat release here. So you see here we have an example, magnesium oxide and water to magnesium hydroxide. So that happens at about 300 degrees. And you have a reaction enthalpy, which you can see down here. So interesting in this context is that basically we have a solid reactant A, and we have a gaseous phase B, for example. So, and what we want to do with these compact thermal energy storage materials, we want to characterize them, we want to develop new, better materials, we want to have an improvement, and finally, we want to test them within an actual component, for example, heat exchanger or a reactor, something like that. So the general approach is material development for improved thermal energy storage performance. So that means we have to quantify the impact of material development on the actual storage performance. So that is not that simple, because the energy density, the value which is most interesting for us, how much energy can we store per volume or per mass, is not a material property. It's very much depending on the process conditions. And that makes it a bit complex, and the material testing under real operation conditions is the only way which delivers maximum values for this energy density. So we have to really look at a certain material under specific operation conditions. So the main questions, we start a bit, what can we expect from material research and development, as I said, PCM and TCM, for the actual performance of these applications. We have to ask ourselves, what are the relevant material properties? How are they linked to the storage capacity, the energy density? And how are they linked to the economics? Because we have to really always keep in mind that it has to be not too expensive. If we find something rather expensive, then it doesn't help at all. So why are the relevant applications and what are the relevant applications and their operation conditions is the last question. So I would now like to maybe show a little bit back in what we have done in the past. So that was very interesting for me as well, because I will start with a topic which is a little bit a failure, because it did not come out as we expected. So it was in the first phase, actually, when we thought, okay, we want to optimize or improve materials, so in order to get high storage capacity. So it's interesting to find out whether there are any theoretical limits of an expected storage capacity. So we looked at phase change materials, and we found some semi-empirical rules for the dependency of energy density on the temperature. As you can see here in the diagram, where we have the enthalpy and the temperature, and there are two rules: the Truton rule and the Richardson rule. The Truton rule is concerning evaporation, but if we talk about phase change and evaporation is nice because there are higher energies involved, but it's hard to handle from an engineering point of view. Richardson rule is about melting, so that's interesting for us. And you see, it fits quite well for elements, including water. As you can see here, here's water, but it's not very good for molecules in general. For example, calcium chloride hexahydrate we have here. So that's a bit out of this approach. For PCM, it's getting much more complex. So here the reaction enthalpy, delta H, is here, as you can see, is a function of temperature and the change in entropy. And the change in entropy is depending very much on the number of the converted mole fractions of the gases involved. I told you about the gaseous phase. So here you can see you have a number of lines for the number of delta S of the change in entropy. And here you see the moles involved, 8 mole gases here and so on. That is also not a clear answer to our question. So I still believe there might be a possibility to define theoretical limits from a thermodynamical approach. But in fact, we had no time to go further into this topic. What we found in general is that for higher storage capacity, higher temperatures are necessary. And that's a little bit too general, but it's not that bad, because it means it's very unlikely to find a material which has a higher storage capacity performing at a lower temperature. But now coming to more successful stories, standard measuring procedures. We found out in the very beginning that when we compared our measurement results, that there are differences, and we made a round-robin test where we sent around a sample of material, here a phase change material, to all the involved institutes and laboratories, and we found that for one material we had a difference in the melting temperature of about 4 Kelvin. So that's not really satisfying. So between 27 and 31 degrees is the melting temperature measured. And what we did after that, we had several workshops with actual, here you can see the measuring equipment. So we had really workshops with this measuring equipment, and we agreed upon standardized measurement procedures. And that helped a lot. As you can see here, now the difference is 0.5 Kelvin. And that's acceptable. I think this is one of our real success stories. Since we have now reliable results for such measurements, the melting temperature, for example, which is very important, also the involved energy and things like that, we said, okay, it would be good to have our own database with these validated data. And we started this activity with the phase change materials. So there is now we have quite a nice database with a lot of information here. And we are ongoing concerning a database for thermochemical reactions, which again is more complex. As you can see here, you have 4 different folders. You can open here the material properties, and then you go to the testing conditions, because thermochemical processes are very much depending on the operation conditions and so on. So this is under construction, I would say. And then a last point, we worked a lot on the operating conditions given by the application. As I said, it's very important in order to really find out or to quantify the improvement by a new material, you have to test it under operation conditions. But what are these operation conditions is the question. And we found out that we had, again, for PCM and TCM, different approaches. For PCM, it's important to have 2 different temperatures, the actual charging temperature and the temperature supplied to the consumer finally. So the actual charging temperature means after any kind of heat exchanger. So it's really the temperature which touches the PCM. For TCM, again, more complex, because here we have the same. We have the temperature, the charging temperature, and the temperature at the consumer side. But at the same time, we need a temperature, ambient temperature during the charging process, or an ambient temperature during the discharging process. These temperatures are standing for the concentration of one of the reactants in this process. So we need at least 4 values describing our process. So just to give you an example, thermal energy storage for solar thermal collectors, for heating of buildings and domestic hot water. So what could be the charging temperature? We had different systems. We looked at actual systems. We looked at and we found out, okay, it's in the range of, let's say, 100 degrees, maybe a little bit lower, 70 to 100 degrees. Here we have some concentrating systems or vacuum tube collectors, so a little bit exotic. So they have higher temperature. But we said, okay, 70 to 100 degrees is the range of our charging temperature. And what we need in the system is between 40 and 65. So that's a low temperature heating system or domestic hot water requirements. And then, as I said, we need these temperature ranges during charging and discharging. And with these 4 numbers, we can now do a testing of the new material. And it's a nice example because for building application, such a definition of reference temperatures is possible. If I now look at, let's say, thermal processes in industry, it is very difficult to really define kind of reference conditions. Okay, so that was the past, and we just started a new task 40 in the ES TCP. And we said, okay, there are still some open questions and still some things to continue. What we want to know within this new phase is to have a better understanding of the factors that influence the storage density and the performance degradation. So this is about stability. We want to still be able to characterize the materials in a reliable and reproducible manner, and not only the properties I showed you. We look now at additional properties like thermal conductivity and things like that. Then a new topic is that we look at methods to determine the state of charge by looking at the material. So that's something where we hope to find some mechanisms to identify the state of charge by properties of the material. And finally, we want to have still a better knowledge on how the design optimized heat exchangers and reactors, how can we really design them and integrate the new materials we found. So this is again the interaction of materials and the components. And following this, we defined different subtasks. So one is material characterization and database. So that's a kind of continuation of what we started. So we want to complete the database as much as possible. Then we have this subtask B. This is about the material improvements. Stefania will talk about that. Subtask C is the state of charge. So we just started with that one. I think we don't have a lot to present today. And then subtask D will be represented by Christoph, stability of PCM and TCM. And finally, this effective component performance with innovative materials. So this is again about how the materials perform within a component. Yeah, and with this, I will close my presentation. So here you see the subtask leaders, if you're interested. And I would answer some questions if there are any, or hand over to Stefania. Or Stephanie.
I'm happy with Stefania as well. Sounds nicer to me.
You're both there.
Well, many thanks for your talk. So just, there was until now no question. I don't see any hand raised, but there is in the chat a quite interesting comment I would like to read from Mark Howitt. He says higher storage capacity may correlate with higher temperatures, but that ignores that these require, ancillary loads to maintain such temperatures. And when the system cools, it needs lots of ancillary load to be reheated. Sorry, I probably pronounced it wrong.
No, I understand.
You know what I mean.
No, maybe I should explain in a few words why I brought this example, because we had a lot of participants interested in absorption material, which can be desorbed at lower temperatures than, for example, zeolite. So let's say not at 300, but at 150 degrees, having the same storage capacity. I mean, the problem is exactly what temperatures do I have and what temperatures do I need? And then, as I said, the other two temperatures important for the describing the process. But the problem is that this theoretical analysis shows us that it's not very likely to find something which can provide higher capacities at lower. So this is not about the system, because this comment is more related to really how to run the system. This is very, very basic and only talking about charging, discharging temperatures and the material. So of course he's absolutely right, but that's a kind of problem which appears later in the development.
Okay, many thanks. I hope it's answered with this. If not, just write in the chat or maybe directly email for any further questions. There's another question from Lars Rönsch. Please go ahead.
Yeah, thank you very much. I was wondering about the role of gaseous pressure in the system of the thermochemical storage materials. I think this is another very important aspect to play around with the temperature level at which you absorb or desorb the gas and thereby perform the heat release or heat storage. This plays a very great role, especially in hydrogen metal reactions. We have been working for more than 15 years in this field, and also in the water metal oxide world, this plays a very big role. And I wonder if you can comment on the role of the gas pressure, actually.
Yeah, no, exactly. So I know that it was much too short, the time, and I was too fast. I have to explain this ambient temperature stands for the concentration from one of the reactant. This is exactly the gas pressure. So talking about water, which is very easy, it's water vapor. And the reason why we took the ambient temperature is, if we have this ambient temperature, it's very easy to provide let's say, connected gas pressure. Yeah, if I have a certain temperature is available from the ambient, I can always provide this gas pressure. So that's the reason why we reduced it to temperature. I know that this is a big step and you have to explain it really carefully, so that this temperature, this ambient temperature, stands for, let's say, really concentration, molecules per something, or gas pressure. So it's all equivalent. You can calculate it in some way. Yeah, so it's a huge simplification, but we did it because otherwise it's getting very difficult to explain why we need these 4 values. But thank you for the question. It was because it was probably not understandable.
Okay, many thanks. So I would like to go to the next topic. There was just one short question about the presentation you shared. If you can forward this to Caspar Mauth-Polsen. Maybe if you're happy, Andreas, you could, if you have time as well, answer directly to the person in the chat, or there was also a second comment, just so that we can stay in time. I would like to move forward to Stefania, please.
Hello, thank you very much. So good afternoon, everybody. As Andrea said, this is I will give you some information about the subtask V that deals with the compact thermal energy storage material improvement. So I would like to give you a general idea about the work we will do within this subtask. So the first, oh God, not working anything, sorry. Yes, now. The first point is why we want to have a material improvement and how we want to do that. And I will give you some idea about the structure of the subtask, the research, and all the participant, the expert that will contribute to it. So first, why? Because as everybody knows, I guess, we would like to have the perfect material that to be used in a real application. We know that we would like to have a high energy storage density, and of course working in a temperature that fulfill the application. The material has to have a fantastic kinetics and controllable. Thermophysical properties very, very good also, so thermal conductivity nice, volume expansion, mechanical properties. Of course, we would like to use this material forever, so a good cycling behavior. The material has to be reversible and not degrade after multiple cycling. The material has to be compatible, so no corrosion with the containment material. And of course, very important, we have to be able to put this material inside a thermal energy storage system. It's going to be very interesting after 3 years to answer to the question if this material improvement will be able to impact on system design and cost. So I think this could be a key point that we could we can look at it during our work up to the end in order to give an answer to that. So how we would like to improve the material? So we are thinking about different strategies. The first one is, of course, we will have a look to new material formulation. So we want to create new material. So this means material with a thermodynamic, a good thermodynamic. We want to modify the thermodynamic to increase the thermal energy storage, the amount of energy we can store, and also the temperature. And we can do that in different ways. For example, we can act on the structure of the material, on the crystalline structure of the material, creating doped material. So, for example, adding new atoms in the structure. We can functionalize, for example, in case of porous material, we can imagine add how to say functionalizes, functional group, sorry, to modify the chemistry and to have a special behavior, the behavior that we want. Or we can act on the microstructure of the material. In this case, we can create nanostructural materials, synthesize nanostructural materials. We know that these materials are very particular. They have very particular reactivity because they are characterized by high defects, very high specific surface area, and this will induce the formation of active sites, giving to the material a very special reactivity. Of course, we have to be, in this case, we have to be able to maintain this nanostructure upon cycling. And sometimes this is not possible, for example, when we work in high temperature. Sometimes we lose that characteristic. We want to increase the energy storage capacity, creating new composites. In this case, we think about different strategies. For example, mixing active materials. This means that the material that are in the composite are both active. Both the material can store energy. We can have porous and organic materials. Of course, in this case, also new composite with high specific surface area, and also nano additives. We can imagine we can add nano additives that have to interact with the material, with the raw material, and somehow to be able to increase the energy, the thermal energy, the capacity to store the energy. Just an example here. We can have, for example, in this case, we have a solid liquid PCM that is encapsulated in an inactive support. We can imagine to do, in the case of mixing active material, to have a solid liquid PCM that is encapsulated or shape stabilized with a solid PCM. In this case, both contribute to the thermal energy. And of course, we have to be sure that the material work in the same range of temperature. The same we can do with the porous material. We can use, in this case, we have absorption materials. We can use as it is, just with the absorption of water, but we can confine into the porous material another active material that will react and will contribute to increase the storage capacity. As I told you before, we would like to have a material with very nice thermophysical properties, so enhance heat and mass transport properties. Also, in this case, we imagine to synthesize composite materials using, for example, highly conductive materials as in this picture. This is can be, for example, expanded graphite in a PCM, or infiltrate the material in a porous media with a high thermal conductivity, for example, metal-based or expanded graphite foams, or also synthesize directly the material into fibers, giving to the composite special thermophysical properties. And at the end, we have to, as I told you before, we have to be able to put the material inside a thermal energy storage system. And in this case, we would like to find the best integration into the application, define the best integration into application. In this case, we will use shape stabilization, granulation with active and inactive binders. This I showed you before this, and a coating on monoliths. Just to picture, we can have encapsulation of the material, we can shape stabilize the material. The shape stabilization, I have to say that is very interesting in case of phase change material, for example, because in this case, it allows you to not dealing with a liquid, because as soon as you created a composite, shape stabilized composite, normally what you want to reach is avoiding leakage from your pellet, your monolith. And often you can do that. So this means that your phase change material will work always, you will see always a solid material, even if you have a solid liquid transition. So this is between the other, it's a very interesting application and way to create materials that can be easily be integrated into the application. So coming back to the general objectives of this subtask, we want to identify strategies to tune the reactivity of this material, to improve the properties and the performances. So we will deal with the discovering of new material. I think this is always something we shouldn't lose. We should keep trying to discover material with better properties. This means to change the chemistry, as I told you before, the structural modification, functionalization of nanostructural material. Then to have new composite with active materials that will help to increase the energy storage density, and then to evaluate the influence. Okay, composite also to improve the thermophysical properties, composite to improve the mechanical properties also, because this is another point, another property that is very important, and to evaluate the influence of the synthesis on the final technical, economic and environmental performance of the material. So we will study sorption materials, we will study reacting materials and phase change materials. At the end of this task, we will have deliverables, so it will be very interesting to build these deliverables together with the expert working in the task, because I think everybody will learn from that. We will learn from each other. This is very important, the last slide of my presentation, that is very important, I think, because in here there are all the experts that are contributing to this subtask. There are the type of materials we will study: phase change material, thermochemistry, thermochemical materials. Here some just the general information about the material we will use, the composite we will consider, and the objectives and the pathways. When I prepared this slide, I realized how many people are working in thermochemistry and how few experts in this task are working in PCM. But I hope that we will, I think it will be very, very interesting interesting work, and it will be very good to work together. So this is the end of my presentation. Thank you very much for your attention. And I will be here if you have questions.
Many thanks for this very interesting overview. There was quite a lot of information in a short time. Not sure if there is any questions, so please raise your hand if there is.
I cannot see anymore anything. No,
not sure. No, so okay, then I might use, yeah, Andreas, please.
Maybe just to add, Stefania said with the last slide, she said a lot of people working in TCM. In the past, it was the other way around. So I think the first two phases, we had much more attendance in the PCM field. So it's okay if it's now the other way around. It's fine.
Yeah. Okay, so it's not an unfair or there's an equilibrium somewhere.
No, it was, I realized it just when I prepared this slide, because I had a list of the people working in that. But it was a list, a table. And then when I prepared the slide, I said, okay, good.
So maybe it's also a good opportunity if there's someone in the audience.
Yes, yes.
I think it's quite open. So I just used the opportunity to ask a question to you directly.
Yeah.
In your opinion, I guess there's a lot of experience you have over the last time working on these fields. What is, in your opinion, the most challenging material property to work on? Which is, I mean, it sounds negative, but it's good because it also means there's a lot of opportunity to win something.
I think I would say the reversibility of the material. For me, the big point is we have these nice materials that have very nice properties for a few number of cycles, for a bit larger number of cycles, but this degradation, I think that is an issue, that is a key issue.
Yeah. Okay. Yeah, many thanks for answering. So yeah, thank you again also for the talk.
Thank you.
Then I would say we can go directly to Christoph. Please, the stage is yours.
Yeah, well, Stefania's comment was a very nice connection to the topic of stability. So why are we interested in stability? That was already mentioned. We want to use the materials for many charging and discharging cycles. And talking about stability, we mean that the initial material properties remain constant, remain as they were at the beginning. And so the subtask D is about first defining stability, and then talking about methods to analyze stability, investigate and understand the relevant degradation processes. So first, related to PCM, the basic question is what affects their stability, the stability of phase change materials. So as already outlined, there are different material classes that are used as PCM, and these material classes, some of them are inorganic materials, some are organic, so they have quite a variety of material properties and phase change behavior. And then applying the materials also in measurements, these PCM are thermally cycled. So thermally cycled, that means starting from a solid which takes up heat, you end up with a liquid phase, and the other way around, the liquid releases the heat of solidification or crystallization, and at the end you have the solid again. So this would be one full thermal cycle. And for PCM, then of course it's relevant that this process happens many times without any degradation, without any negative change in the phase change behavior. So what can happen? two examples of degradation on the left side. This is very popular for organic materials. Here the example is taken from the final report of the previous task phase. And you see a sugar alcohol, D-mannitol, after exposure at high temperatures for some days. And what you see is what you usually observe in the kitchen, maybe. It looks like caramel, what is maybe nice in terms of sweets, but not desired when you want to use it as a thermal energy storage material. So this is typically for organic material, the chemical degradation at high temperatures. A second type of degradation can be observed for mixtures or salt hydrates. Well, salt hydrates are also mixtures of salts and water. And here what can happen is that you have a separation of different phases after repeated melting and solidification transitions. And shown here is a picture taken from a thermal cycling device, and you see two different solid phases and a liquid phase in between, which is also unwanted. In the previous phase, the starting point in terms of stability was this work. We collected and compared several devices, experimental testing devices from the participating experts, and wrote this open access paper that you're welcome to have a look at. So this was for us a starting point to go a bit deeper in the topic of stability and degradation phenomena. Coming to TCM, what affects their stability? So again, as also Stefania showed, there are different material classes and especially composite materials nowadays investigated as TCM. You see here examples of the pelletized zeolites as sorption materials, and then some examples for composite materials for chemical reactions. And the difference compared to PCM is that these TCM are not only subject to heat transfer, but also to mass transfer processes. So heat and mass transfer occurs in applications. For example, the working couple zeolite water, it's not only that you heat it up and cool it down, but you also supply humid air to the zeolite, or you take the humidity out of it for charging and discharging respectively. So these heat and mass transfer can cause different degradation processes. Two examples for sorption materials are shown here. So for example, looking at the pictures on the left, you see here pellets of zeolites that are broken up by hydrothermal aging. Hydrothermal, so high temperatures, high humidities, and then these these spheres, these pellets deteriorate. You see on the left, the outer pellet surface is broken, and the picture on the right with advanced degradation, you see that also the structure of the cubes is rounded, is degrading. And such a degradation can lead to reduced water uptake of the zeolite, but it hasn't to be as worse as shown on the left side. You can also have a change in the inner crystalline structure. For example, a transition to an amorphous phase, and that was investigated here on the right side, where the material was aged under different hydrothermal conditions, and it was found out that the reduced water uptake strongly correlates with the temperature and the water vapor pressure, while the worst degradation was observed for the highest water vapor pressure at lower temperatures. So those are two examples. The activities and objectives now in Subtask D of task 40 are listed here. So as a starting point, we want to establish a common definition for PCM and TCM stability, as we found out that the wording is quite diverse. So for us, it's important to have a common understanding of these stability-related questions. The second activity is then to identify and describe the most relevant degradation mechanisms. And this has to be done for each material class separately. So here for PCM and TCM, the material classes are listed that are investigated by the experts of the task group. Activity 3 is then to find out how degradation can be accelerated in order to faster assess the stability. So if this is possible at all. And well, bringing all this together, we would like to develop recommendations for stability testing that is based ideally on simple and rather short-term experiments. We also have 2 planned deliverables. First one is the description of PCM and TCM degradation mechanisms that might be a review paper depending on the amount of work we want to put into. And the second outcome is a, let's say, step-by-step recommendations for stability testing of PCM and TCM and the, let's say, popular material classes. And the first action, yeah, I already mentioned the importance to work on a common wording. You see here some of the terms that are not consistently used, but should be agreed upon. And the second action is a continuation of these stability testing device papers. So we want to make an inventory on the existing equipment and expertise in the field of PCM and TCM stability, and especially the first action can also be an input to the PCM TCM wiki at the materials database. At the kickoff meeting of the task in October last year, we already started with the discussion of possible key messages, and well, in some cases it's more key questions for now. So, and with those questions, I like to come to the end to the presentation because I think they show the broad field of discussions which we usually have at these task meetings. So a first point is, of course, to create an awareness of stability problems related to certain material classes. And then we, in the discussion, we found out that there are always two perspectives or 2 motivations to investigate stability. It's for material development, but also relevant for storage prototype testing. Then one key question is if it's possible to accelerate degradation and thereby to accelerate the testing itself. If this is possible and meaningful, that means if the relevant degradation processes are covered by the experiments. And also related to accelerating is the question if there are kinetic models that can be used to extrapolate degradation and thereby to predict PCM and TCM stability during the lifetime. Yeah, as already said, we want to look at the different degradation processes. So it's important to test stability with knowing which processes are involved. And that means that you need to have methods that can separately investigate different degradation processes. And then this is also in connection to the subtask E on material component interaction. It's also important to assess the stability of these materials by testing within components. The components means heat exchangers and reactors. And it's also, yeah, wanted to find out for which material classes the stability depends on the scale of the tested samples and also on the conditions of the components they are tested in. So with this colored overview of key messages and questions, I like to come to the end of the presentation. Thanks for your attention. Thanks to the many contributors of this subtasks, which I haven't listed here, but yeah, thanks to them as well. And I'm happy to answer questions.
So yeah, many thanks, Christoph, for your talk. Again, a nice overview of what's happening and the challenges. We have one question in the chat. So there's written, Mika Sender here, any thoughts on testing or tactics? Additionally, any exploration ideas for rapid cycle testing?
Well, eutectics are of course one of our main interests as well. Eutectic salt hydrate mixtures, and yeah, theoretically, a eutectic should be thermally cycling stable. But what we found out, not only what we found out, but many others too, is that if the different components forming the eutectic have a varying crystallization speed, then there is the possibility that you will have separation and degradation even for eutectics. So if it's not a, let's say, if it's not a single pure component, then cycling stability is always an issue. Yeah.
Okay, many thanks.
And rapid cyclic testing, well, yeah, there's a lot of literature on rapid testing. And again, to clarify this, the main idea is not to have rapid testing, but to speed up the relevant degradation processes. So it's not meaningful to have rapid cycles without, let's say, without covering or considering the relevant degradation effects. So you can have a, let's say, a quick test without having any valuable output of it, if it's just fast and yeah, fast testing.
Yes, many thanks. So it has its drawbacks. There was another question. Is how long will the life of the PM reach for practical application?
The PM is probably the PCM, so
Yes,
that depends on the material class and strongly also on the operation conditions. So for some material classes, high temperatures are the problem, as I showed for the organics. For others, it's more the cycling. And but yeah, Harald also commented it. So there are materials and also certified products with 10,000s of cycles.
okay, good. So many thanks. I guess we can close here if there are not further questions. So just let me share my screen as well to make the advertisement for the next one. So yes, next month there will be the next OnSeminar, also on the 17th. So 17th of March, also Thursday at 14 o'clock CET. This will be quite interesting, like let's say some future perspectives about the new ideas in the energy storage TCP. So there will be the three topics: the economics, the medium duration storage, and the building mass utilization. The speakers will be, I mean, could be there are some changes, but as far as it's decided now, it's Christoph Rathgeber again, many thanks already, Georgina Morris, Seamus Garvey, and Jonathan Radcliffe, and Christoph Rodinger. So I'm very happy if you join again. And as last time, the recordings of this session will be distributed to the people in the mailing list. And for any further questions, just write to the ESTCP secretary. We are happy to answer. And with this, many thanks and have a good day.